Okay, so shall we start?
Mhm.
Okay. So I want to distribute to you the formula sheet and then the questions and solutions. I will give you the exact formula sheet on the exam. So you don't have to memorize the formulas, but you should know how to use them and what they mean. So the quality problems and their solutions are already on the blackboard. So I want to start with a refresher on the normal distribution. There are two types of normal distribution. One is the standard normal distribution. Okay. So what are the properties of the standard normal distribution? The mean of the standard normal is 0, and the standard deviation equals 1. And then there's any normal distribution. Okay. So any normal distribution is something that I made up. Okay. So the mean can be any number. Okay. And then the standard deviation can be any number also. Okay, so standard normal, any normal. So we can go from any normal distribution to standard normal, and from standard normal to any normal distribution. How so? So let's suppose you have a z value here, and you have an x value here. Okay. So for each z value on the standard normal, you will have an x value on any normal distribution. Okay. So these two normal distributions correspond to each other. Okay. Please take a formula sheet and questions with solutions. So these two numbers, x and z, correspond to each other. How do we, excuse me, how do we know they correspond to each other? Because they have the same tail probability. So this tail probability and this tail probability are the same. Okay. So we don't know the probabilities for any normal distribution. We only know the probabilities for the standard normal distribution. But that is fine because from any normal distribution, we can go to the standard normal and we can find the probability. Okay? So the probabilities of the standard normal are given in a table. Okay? So as long as we know the standard normal probabilities, we can find out probabilities for any normal distribution. Okay. So let's start with the questions. So the first question says, specifications for a part for a DVD player state that the part should weigh between 24 and 25 ounces. The process that produces the parts yields a mean of 24.5 ounces and a standard deviation of 0.2 ounces. The distribution of the output is normal. Okay? So the first question, part A, asks, what percentage of parts will not meet weight specifications? Okay, so let's draw the uh, let's draw the normal distribution, okay? So the mean of the distribution is 24.5, okay? And the standard deviation is 0.2, okay? Sigma equals 0.2, okay? And we are given two limits, okay? We are given two limits, 24 and 25, okay? So this is 24, this is 25, okay? So now the question is, what percentage of parts will not meet weight specifications? So basically, if a part weighs more than 25 ounces, it's going to be too heavy. If a part weighs less than 24 ounces, it's going to be too light. Okay? And the question is, what percent of parts will be either too heavy or too light? Okay? Is everybody clear on this? Okay. So so this is not the standard normal distribution. Why? Because the mean is not 0 and the standard deviation is not 1. Okay, so this is any normal distribution. So let's find the standard normal here. Okay, so I'm going to, so the standard normal will be here, something like this. Okay, u0, sigma equals 1. So to find this tail probability, okay, so we need to go, so this is x, okay, we need to find the z that corresponds to this x, okay, and this tail probability and this tail probability will be the same, okay. So what is the formula? The formula is this, z equals x minus mu divided by sigma square root of n. This is the formula. This is also on your formula sheet, right? So here we know x, 25, x is given. Mu is also given, 24.5. Sigma is also given, 0.2. And now we need to find out what n is. Okay, n is the sample size. Okay. Now in part A, we don't have a sample. In part B, we have a sample. Okay. So in part B, it says we have this sample of size 16. Okay. Sample of size 16. Okay. But that's for part B. In part A, we don't have samples. We are measuring individual parts. Okay. What percentage of parts means we're measuring the weight of individual parts. So that means n equals 1. Okay. So n equals 1. Because every part is its own sample. Okay. So I hope this is recording fine. Looks okay. All right. So let's find the z value here. Okay. which z-value corresponds to x equals 25. So for that, I plug in the numbers. X is 25, mu is 24.5, divided by sigma is 0.2, square root of 1. Okay. So this is going to be 0.5 divided by 0.2 equals 2.5. Okay, so the z-value that corresponds to the x value is 2.5. So if we find this tail probability, we will also have found this tail probability. Okay? So for that, we look at the formula sheet. At the back of the formula sheet, there is the standard normal distribution. Okay? And we are looking for 2.5. Okay? And it says 2.5 is this much. Okay? So what this really means is the following. So here's the standard normal distribution. Okay? Here is z equals 2.5. Okay? So this is the tail probability. Okay? Now, this the area under the curve to the left, which I call the belly probability. Okay, this is not a formal statistical term, but I call this the belly probability, is 0.9938. So 0.9938. This is the belly probability. Okay? So if this is the belly probability, what is the tail probability? Okay? So the tail probability will be 1 minus 0.9938. And that equals 0.0062. So the tail probability of z equals 2.5 is 0.0062. 0.0062. Okay, so this tail probability here. So if this tail probability is 0.0062, then this must also be 0.0062. Because this z corresponds to this x, and therefore this tail probability will be the same as this tail probability. Okay? So we know this portion of parts, individual parts, will be too heavy. Let's find the portion of parts that are too light. Okay? So in this case, x is 24. What will the z value be? So we use the same formula, z equals x minus mu divided by sigma square root of n. Okay? So this is going to be 24 minus 24.5 divided by 0.2 divided by square root of 1, and this is going to be minus 2.5. Okay, minus 2.5. Okay. So the z value that corresponds to x equals 24 is minus 2.5. Okay. So if you look at the standard normal table on the back of the formula sheet, you will not find negative numbers. But that's okay because all normal distributions are symmetric. Okay, so any normal distribution is symmetric, standard normal distribution is symmetric, all normal distributions are symmetric. What does that mean? 2.5 and negative 2.5 will have the same tail probability. Okay, so I don't even have to look this up because of symmetry. Here, 2.5 and minus 2.5. Because of symmetry, they will have the same tail probability. Okay, so we know this tail probability, and from here we can go to this tail probability. Okay, so that means 0.0062. So, and then the question says what percentage of parts will not meet weight specifications. We need to add these two numbers up, okay? So 0.0062 plus 0.0062 equals 0.0124 or 1.24%. So 1.24% of parts will not meet the weight specifications. They will be either too heavy or too light. Okay. Is everybody clear on this? Okay. So let's go to part B. In part B, the question asks, so first of all, in part B, we have samples, okay? So we take samples, and each sample has 16 items in it, okay? So n equals 16. Within what values will 95.44% of sample means of this process fall? So let's draw this again. Okay. So here we have this process. The mean is 24.5, sigma 0.2, n equals 16. Okay. So there will be two control limits, upper control limit and lower control limit. Okay. So what are the values for upper and lower control limits such that the percent of sample means, okay, so the shaded area is 95.44%. So this area, the shaded area, will be 9544. Okay. So if we know the so-called Bailey probability, can we find tail probabilities? Okay. Can we find tail probabilities? Yes, because if we take 1 minus the Bailey probability, we will have the tails. Okay, so we're going to say 1 minus 0.9544. Okay, equals. I think this is going to be 0.0456. Okay. But this is the sum of two tail probabilities, right tail and left tail. So each tail will have half of this, so 0.0456. divided by 2.0228. Okay, so this is going to be the probability of each tail, 0.0228. This is going to be 0.0028. Okay. So let's find the corresponding value, z value, for the upper control limit. Okay. So this z value corresponds to this upper control limit, where the tail probability is 0.0228. Okay. So the standard normal table does not give us the tail probability. It gives us the belly probability. So the belly probability will be 1 minus this. Okay. So the belly probability will be 0.9772 for this particular z, which corresponds to our upper limit. Okay. So let's look up this value. Okay. Okay. So as you can see, it's here, 0.9772. Z equals 2. Okay. Okay. So here, 0.9772. So this is what we're trying to find. It's here, 0.9772, and it corresponds to 2. Okay. So we can go from z to x, okay, which is our upper control limit. The formula is this, mu plus z times sigma square root of n. So mu is 24.5 plus z is 2, sigma is 0.2, square root of n is 16. So mu 24.5, okay, z is 2. We just found out z was 2. Z equals 2. Sigma is given in the question, and is also given in the question. And the answer to this will be 24.6. Okay? So that means our upper control limit will be 24.6. Any questions? Okay. All right. So we have found the upper control limit. Okay. So then we need to find the lower control limit. Okay. So the z value that corresponds to the lower control limit will have the same probability as this one. So 0.228. 0.228. Okay. Because if these two numbers correspond to each other, they should have the same tail probability. Okay. 2, okay, 8. So what is the z-value? That corresponds to this tail probability. Again, we see symmetry, same tail probability. And so if these two numbers have the same tail probability, one is 2, then the other one must be minus 2. Same tail probability, minus 2. And then we're going to use the same equation okay. So mu is 24.5 times plus z is minus 2, sigma is 0.2 square root of 16. Okay. And then when you work this out, it comes out to be 24.4. Okay. So the lower control limit will be 24.4. Is this clear to everybody? Okay. So let's go to question 2. Okay. In question 2, let me erase this real quick. Okay. So an automatic filling machine is used to fill 1-liter bottles of cola. The machine's output is approximately normal with a mean of 1.0 liter and a standard deviation of 0.01 liter, blah, blah. Samples of 25, determine the upper and lower control limits. That will include roughly 97% of the sample means when the process is in control. So we're going to do the exact same thing, right? So we have a process, okay? We're going to have a mean, which is given as 1, standard deviation sigma 0.01, n is 25. We have an upper control limit. We have a lower control limit. And the belly probability is 97%. So the shaded area will be 97%. Okay. So if the shaded area is 97%, the tail probabilities will be 3%. Okay. So 1 minus 0.97, the tail probabilities will be 0.03 or 3%. And each tail will have half of this. So 0.03 divided by 2 is going to be 0.015. Okay? So this tail probability will be 0.015. This tail probability will be 0.015. Okay? So then we can go to the standard normal. Okay. So we want to find the z-value that corresponds to the upper control limit. So which value of z corresponds to the upper control limit? For that, the tail probability must be 0.015, And the belly probability will be 1 minus 0.015, which is 0.985. This is the belly probability. Okay? So we need to find this belly probability, and then from there we can go to the z value. Okay, so let's go to the back here. 8, 5. Okay, so this is the value. This is the belly probability that we're looking for. 0.985.